In this video, we're going to look at the section 5.3 topic, Conditional Probability and Independence. How about that? There's a bell. Two events are independent if the occurrence of one event does not change the probability that the other event will happen. So this is the key. One event does not change the probability of the other. To test for independence, let's define events A and B. Events A and B are independent if probability of A given B is equal to probability of A, and probability of B given A is equal to probability of B. The given would be the event that happens first. So let's check rolling 2 3s in a row. So let's say that event A is rolling the first die, or the first 3, and B is the second 3. So what we want to know is, does rolling the first 3 affect the probability of rolling the second 3? So if we just said, what's the probability of rolling a 3? Probability of rolling a 3 would just be 1 out of 6 if we just rolled a 3 by itself. But what's the probability of B given A? In other words, what's the probability of rolling a second 3 given that I've already rolled the first 3? Well, you know that there's no difference. They are the same. Since 1/6 equals 1/6, then these events are independent. Now chances are you won't be called on to prove that rolling 2 dice are independent, because that is a known independent event, common sense. But that's just an example of how we can prove it using the definition of independence. Drawing 2 3s in a row from a deck of cards. So let's do this again. So probability, so A would be the first 3 and B would be the second 3. So just the probability of drawing a 3 from a deck of cards would be 4 out of 51, or 52, sorry, 52 cards, and there's 4 3s. But the probability, so this is B actually, so the probability of A given B, what's the probability of, probability of B given A? The probability of B given A, what's the probability of drawing a second 3 given that I've already drawn a first 3? Well, once I've drawn a first 3 out, there's only 51 cards left, and there's only 3 3s left. So since 4 out of 52 does not equal 3 out of 51, these events are not independent. Okay, let's look at the thing we did in the previous video with Federer and making serves and making points. So let's say that the probability of that A is making his first serve, okay, and that B is scoring a point. So let's just look at what the probability of B is overall. What's the probability that he scores a point? Remember, we had to look at that adding these two together. The probability that he wins a point is the sum of these two. We have this written down here. The probability that he wins the point is 0.7023. What is the probability that he scores a point given that he makes his first serve? Well, that's different. The probability that he scores a point given that he makes his first serve is 0.78. We can also look at the probability that he scores a point given that he does not make his first serve, which is 0.57. Notice none of these are equal to each other, so the events making his first serve and Federer scoring a point are not independent. Whether or not he makes his first serve affects whether the probability of his scoring a point. Now this is kind of unusual. Let's say event A, well actually let's just call this M. M is being male, P is being pregnant. So for the sake of argument, let's just say that the probability of being male is 0.5. Okay, so that's probably not exactly true, but like people in general, we'll just say there's about a 50% chance of randomly selecting a person and they're male. What's the probability of randomly selecting a male given that the person is pregnant? Well, that's 0. 0.5 is clearly not equal to 0, so the events being male and being pregnant are not independent. Now, that may be confusing to you because you think of those as being independent, but what you're really thinking of is the fact that they are mutually exclusive. Being male and being pregnant cannot happen at the same time. They're mutually exclusive. Since they can't happen at the same time, the probability of one happening if the other happens is 0, which makes it different from either one happening by itself. So based on the definition of independence, the events are not independent when they're mutually exclusive. Now let's look at a table of data, two-way table, which shows person's gender and whether or not their dominant hand is their right hand or their left hand. Is there an association between gender and being left or right-handed? A simple random sample of 100 Australian high school students was selected from among survey participants at the Census at School website to answer this question. Use the independence test to see if being male and being left-handed are independent. So we can do it either way, but I'm going to do this. I'm going to look at probability of left-handed and then probability of left-handed given that you're male. And I could do it the other way around, but this makes sense to do it this way to me. So probability of being left-handed is 10 out of 100 or 0.1. The probability of being left-handed given that you're male is 7 out of 46. Okay, so we're looking at only the males. And I think I did this on my calculator earlier. Yeah, that's 0.15. So 0.15. Okay, so I need to make a conclusion here. Since 0.1 is not equal to 0.15, being male and being left-handed are not independent. In fact, looking at this data, it appears that being male or being left-handed is a little more common if you are male than if you are, or being male makes it more likely to be left-handed. Okay, because 10% of people overall are left-handed, but in the sample, 15% of males are left-handed. So I can say in this sample, males are more likely to be left-handed. So there does seem to be an association. Now a little bit more summarizing independence. We talked about the pregnant versus the male. So let's say this is male and this is being pregnant. Now we said, let's just assume for the sake of argument that we have a group of people and 50% of them are male and let's say 2% of them are pregnant, which means the other 48% are not male or not pregnant, and not pregnant. They're females who are not pregnant. Now we see there's no overlap. These two groups are mutually exclusive. It means they cannot happen at the same time. So remember we said the probability of male is 0.5. The probability that you are male given that you are pregnant is 0. Since 0.5 does not equal to 0, these events are independent. And it turns out that mutually exclusive or disjoint events are never independent, because if one happens, the other cannot happen. Okay? So the probability of being pregnant is 0.02. The probability of being pregnant given that you're male is 0. Once again, they're not equal to each other.